Welcome to EDU World Space.
So in this problem, you have a star and a spaceship moving away from the star at a certain velocity v, which is not given. And this spaceship or this star is measured to be 6 light years away from the Earth in the Earth's reference frame. In the spacecraft's reference frame, they measure a time of 3.5 years for it to reach the Earth. And what you want first is to find the time that clocks on Earth in Earth's reference frame would measure the spacecraft to have taken once it completes its journey. Right. So for part A, you first need the equation of time dilation in special relativity, which is 26-1a, and that is given by this formula over here, TE, which is the velocity measured, the time measured at Earth, equals gamma times TS, which is the time measured at the spacecraft. Gamma is 1 over square root of 1 minus v squared over c squared. So this is simply TS over square root of 1 minus v squared over c squared. Okay. So you have this is one equation that we use. The other equation we're going to use is this velocity, which is given by the distance measured from the Earth's reference frame over the time measured from the Earth's reference frame. Now, it is super important to note here one key fact about this problem, and indeed about all of special relativity, which is that the relative speed can be calculated in either reference frame and will be the same in both frames. So this v over here will be the same whether you're in the Earth's reference frame or in the spacecraft's reference frame. Okay? And so using this equation and this one over here, we get that delta, sorry, shouldn't be a delta, should just be a t. We get that time from Earth's reference frame is equal to time from spacecraft's reference frame over square root of 1 minus v squared over c squared, which is equal to, from this velocity equation here, Ts over square root of 1 minus, remember v is Le over Te, so 1 minus Le over c times Te squared. We're simply replacing the v here with Le over Te, okay? And so then you square both sides, right? And you get Te squared equals Ts squared over 1 minus Le over c times Te, this thing squared. And you rearrange some terms here, and eventually, doing just a little algebra, you'll end up with Te squared will be equal to Ts squared plus LE over C quantity squared. Okay, and so Ts squared we already have, that's 3.5 years, square that, plus LE will be 6 light years, but a light year is just light traveling at velocity c in 1 year. That's the distance light travels in 1 year. So 6c times 1 year over c squared, and your c's cancel, and eventually you will get, you work this out, you get TE, time measured from Earth, to be 6.95 years. Okay. For part B, you want the distance that the spaceship travels as measured in its own reference frame. So this is L sub s, right? And very importantly here, recall that relative speed can be calculated in either frame, and it will be the same in both frames. So what this means is that you have v equals the distance measured in Earth's frame over time measured in Earth's frame to be equal to distance traveled, distance measured in the spacecraft's frame here, L sub s, sorry, over the time measured by the spacecraft, which is T sub s, okay? And so to find L sub s, you simply rearrange that equation. You get L sub e times T sub s over T sub e. And this will be 3.5 years over 6.95 years, so the years cancel, times 6 light years, which is L sub e. And so you get something in units of light years, and that something is 3.0 light years. And this is the same, this answer is the same as that which you would find if you use the length contraction formula, which simply relates the lengths in different reference frames. Okay, so there's that.